let's take a moment to look at our last part of momentum here. Momentum in collisions. Both elastic and inelastic collisions will be the ones we're looking at. First thing I want to do is just to talk about those objectives for today. We're really going to look at both types of collisions, elastic and inelastic, and calculate both momentum and energy with each one. We also want to describe the momentum of each object in a system as the product of its mass and velocity. And we really want to use those mathematical representations. And to identify the claim that the conservation of momentum, or really the momentum before equals the momentum after, indicating that the total momentum of a system of two interacting objects is constant if there's no force on the system. So first thing we want to do is to do a little review. And I've got a green part here, and I've got a blue part, and I also have a red part. And what I want you to do is to take a moment and pause and see if you can do all of these as a quick review beforehand. So go ahead and pause now. Alright, now that you've paused, let's take a look at that first one here. Calculate the momentum of each of the following objects. Here we've got the 0.5 kilogram, we've got a mass and a velocity. We plug into our momentum formula, and remember, this kilograms per meter, kilograms times meters per second can really also be written as something like this, our kilogram meter per second. Try the second one. So a 25,000 kilogram bus, we've got a mass and a speed. This time we can plug it in to find our momentum. The third one, looking at an electron traveling at a very fast speed, and we know that the mass of an electron is very small, so we're going to multiply those two together. We can really multiply our 9.1 times 2 first and add our exponents together to get our 18.2 times 10 to the minus 24th, or we could move that over 1, making it smaller, and say that it's 1.82 times 10 to the minus 25th kilogram meters per second. We also want to look at the equations for kinematics here, because we're going to do a little bit of review with these. So what's the S stand for? Well, S stands for distance. What about the U? What about the V? What about the A and the T? Well, hopefully you got these right. A little review there for you. And the last one, we're really talking about recall the formulas for potential and kinetic energy. So what's the formula for potential energy? Well, our formula for potential energy is going to be our mass times gravity times height. And the formula for kinetic energy, which is the one we're going to use today, is going to be our 1/2 times the mass times the velocity squared. So it really has our mass and velocity in it. We've been saying that the momentum before a collision equals the momentum of after a collision, but when does it actually work? When is it actually conserved in our lives? Well, when there are no outside forces on the system. And that's really what we want to talk about, is what's the system here in this case. Technically speaking, when the net external force on a system is 0, the system is described as an isolated system, and that's when our conservation of momentum really applies. So the momentum of any closed or isolated system does not change. Same thing we've been talking about before, and now we're just defining it a little more specifically. So the system of it. A closed system has to be clearly defined. So here we've got a baseball player, we've got a bat, we've got a ball. A baseball is not just a closed system because the bat comes into the baseball's system. So in this case, we couldn't just define the system as a baseball. We actually have to include all the objects inside of it that are coming in contact with each other, or the forces that are really involved here. So alternately, two rolling spheres can be looked at as a closed system. We can say that the forces that are going to be happening and being exerted will be only in this system. Now really, no system on Earth can really be isolated, because there are always some interactions between the system and some surroundings, like you and the Earth, or the the baseball player and the Earth, but these interactions are small enough in most cases to be ignored when we're actually solving physics problems like this. So an example of a system would be this boy and this girl. Can you identify their velocities or their relative velocities? You'll notice they're both on wheels here. And so as there's a force involved, you'll notice that they move. One moves one way, one moves the other way. Can you identify their velocities? Is there anything that you would think about when looking at this system and saying, how are their velocities going to be different from each other? We can assume that they're skating on a smooth surface with no external forces. We really would say that there's no friction involved. They both start at rest. And their velocities really depend on the relative masses. So because the skater has a mass of this, and the skater D, or the second skater, has a mass of this, then the ratio of their velocities are going to be the ratio of those masses together. So the velocities will be in the same ratio as their masses. Going back to our momentum equals mass times velocity. So really two types of collisions are the things that we want to look at. We've got springy and elastic. Springy, elastic collisions, as well as sticky or inelastic collisions. With springy collisions, momentum is conserved. The collisions are springy and the objects are separate. There's no deformation. So this is going to be like our pool balls or billiard balls where they run into each other. They do not break or deform. They separate from each other. The collisions look like they're springy. The momentum is always conserved. And what about sticky or inelastic collisions? You can see one over here where the two objects actually combine their masses after they have collided together. Well, in this case, momentum is also conserved. So this is something that both of them share. The collisions in this case are going to be sticky, and deformation happens, and the masses combine. So this is really the difference between these two. Let's look a little more closely at each one. With springy or elastic collisions, you can see the car and the truck down here. As they run into each other, the objects are separate. No deformation happens. It's almost like they sort of bounce off of each other. The other thing we can look at is we can look at gas molecules. Gas molecules in an ideal gas bounce off of each other with no external forces. They are very springy. There's no deformation in those molecules. For sticky or inelastic collisions, we can see that now the car and the truck, when they run into each other, they actually stick together. The collisions are sticky and deformation happens. So you can see the front of the truck, he actually runs into these two, and you'll notice there's some speed shown over here where he changes a distance per unit of time. You'll notice that speed, when they add together, is smaller once they run into the truck. So really the objects combine, and that's what we're really going to be looking at next, is how the speed changes. The car and the truck stick together, or we could say something like a baseball being thrown into a cardboard box like this. You can see the cardboard box actually moves a certain distance. Well, that force on the box times time is going to be equal to that impulse change, as you can remember from before. So our force times time is going to equal our mass times velocity in this case. So we'll be able to find the collision of those two, or find the energy or the energy loss in them as well. So ball in the box, they are both going to stick together. Here's an example of a pool shot. You'll notice one ball hits the other, and all the energy is transferred into the 8-ball, or the black ball here. The white ball is actually stopped after it's been going very fast. So it's interesting, the moving ball stops dead and the rest of it moves at the same velocity as the original ball. This is what we're talking about with springy or elastic collisions. All the energy is going to be transferred. So the collision in this case it's a special type of collision. This doesn't usually happen in our world, but here you can see a real world example of it. If one ball strikes the other, they have to be head on in this case, and the moving ball must not be given any spin. So you can actually put spin on it in the game of pool and snooker to actually do different things with the ball and make the ball do different things. But in this case, if we're just wanting it to stop, then we need to have it have no spin on it at this point. So is this springy or is this sticky? Well, I think we answered that one already. Here we have a bouncy elastic collision between two equal masses. You notice as one mass is stopped over here, one mass comes in with a velocity of v. Well, this one stops. The one that was at rest now has that energy. It's almost like they're sliding on frictionless ice, and this only works in a frictionless environment too. It works with friction in our world, but remember that friction is going to take away some of that energy. In this case, all the energy is transferred between these two masses. So the motion of one cart is really transferred to the other. The overall momentum is constant, just like we've been saying before. So with bouncy collisions, you'll notice first the energy starts here with the black mass and goes into the blue mass, and the black mass then stops and all the energy goes off with the blue mass. In all these examples I'm about to show you, the masses are the same. In every case the momentum is conserved. Let's look at another example here where we've got traveling in different directions. So this mass comes in with a velocity, and you'll notice that that velocity, v, is transferred to the blue one, and it moves away with velocity v. The blue mass comes in with velocity half of v, or v over 2, and that v over 2 velocity is transferred to the black mass going that same direction. So you can see how the energy is transferred. Now in this case we have two masses that are going the same direction. We've got one that's moving with half of v, or v over 2, and the other one that's moving with velocity v. So you'll notice the velocity v gets transferred to the blue box, and the half the velocity then is transferred to the black box. Interesting stuff with momentum here. Alright, let's take a moment to look at elastic collisions, or an example of calculating the momentum of an elastic collision. We can see that all energy transferred. In other words, pool and snooker balls are going to have all that energy transferred from one to the other. So our formula is going to be the same. It's going to be the m1v1 plus m2v2 equals our m1v1 plus m2v2 before and after the equation. So we can set those two equal to each other, because we know that if no forces act on this, then they should be equal to each other. So what we're going to do is we're going to replace that v with a u, because we remember from SUVAT that the initial velocity is going to be u, whereas final velocity is going to be v, so we can actually add in our u's and v's here. Take a moment to read over the question and pause the video now. Alright, now that you've tried it, let's take a moment to actually solve it. What we're going to do is we're actually just going to plug in our masses and our velocities before and after, and you'll notice the pattern here. So in this case our momentum is conserved. Now let's try one with kinetic energy, or in other words the kinetic energy of an elastic or bouncy collision. Once again, all the energy is going to be transferred, or in other words the kinetic energy of motion is going to be transferred from one to the other, and we saw that in the last equation. The formula for kinetic energy is going to be our 1/2 mv squared, and we remember that from our review in the beginning. So just like momentum, we calculate it before and after the collision. And so what we're going to do is we're going to take our kinetic energy of A plus the kinetic energy of B and set it equal to the kinetic energy of A and B after the collision. So we'll end up with something that looks like this. But remember that kinetic energy is scalar, so we're not actually going to put any negative signs in here if it's going left or right. It doesn't matter. We're just calculating kinetic energy, and kinetic energy is scalar, which means it's not a vector quantity. So same question as before, but this time we're actually calculating kinetic energy. Pause the video now and try it out. See if you can solve it. Alright, now that you've tried it out, let's plug in our numbers here. We're going to plug in 1/2 mv squared plus 1/2 mv squared and set it equal to the same thing on the other side using our final velocities to find 17 joules, and the kinetic energy is conserved. Let's take a look at an example of an elastic and inelastic collision. So in this case, what we're going to do is we're going to look at our elastic and inelastic video.
Here's an example of an elastic collision where kinetic energy and momentum are conserved. This is an example of an inelastic collision where only momentum is conserved.
I like that because then their speed is very evident that it's slower afterwards. Very fun stuff. So for those inelastic collisions, those are the ones that we saw in the second example. Remember, they're sticky, that momentum is always conserved, that collisions are sticky, and some deformation happens, and always the objects combine. What we're going to find is that when the objects combine with each other, that their masses are going to be added together. So let's say in sticky masses, take a look at what happens here. We've got one block that comes in with a velocity of v, one block that's stopped, and now the two of them together have half the velocity, which makes sense if we remember our ratio of p equals mv. So momentum is conserved again. Once again, we have these as our real relationship of mass and velocity. But since they have the same final velocity, we actually have that last velocity, this v1 final and this v2 final, well, they're the same. There's just v final now. So we've added the masses together and kept their final velocities. So let's try an example here. Take a moment to pause the video after you've read over the question. Alright, now that you've paused the video, let's actually take a moment to see what we have here. Well, we know that the first mass is 800, the second mass is 1200, and our initial speed is 15 meters per second of the first object, the first vehicle, and the initial speed of the second vehicle is going to be 5 meters per second. And so they're moving in the same direction. Let's just assume in this case they're moving to the right. If you can, pause now and try this problem now. If you still need a hint, I'm going to give you one more hint. Alright, if you've tried it out, here comes the second hint. You can use this formula. Now, if you haven't tried it yet, you've got to try it now. Plug in your answers. Pause the video. Alright, now that you've paused the video, let's take a look at what's going on here. What we're going to do is we're going to multiply our mass times our velocity with our mass times our velocity, and we're going to add in to find that final velocity on this side over here. So we'll add our masses together. We've got our 12,000 and 6,000 added together to give us 18,000. Our 18,000 equals 2,000 VF. We'll divide the VF side by 2,000, and we'll divide the 18,000 by 2,000 as well to get VF alone by itself. Once VF is alone by itself, we can solve for that final velocity of 9 meters per second. As you remember, in inelastic collisions, energy is not always conserved. Here you can see some of the energy actually going into crumpling the car or deforming the car. Some of the energy went into breaking some of the windows. So the material that the car is made of may actually get warm or hot. Where did that energy come from? Well, it was from the motion or the kinetic energy. It was changed into thermal energy. Some energy may also be lost in the sound of it. So anytime that there is a very loud sound like a jet flying by or cars smashing together, some of that energy came from the energy of motion or kinetic energy. Crash. So let's try an example problem. A vehicle of mass 800 kilograms. In fact, this is the same problem that we had. But now what we're going to do is, instead of calculating the momentum change, we're going to look at the kinetic energy before and after the collision and the loss of kinetic energy. So as we have two objects that are going to be running into each other, see if you can pause this video and try it now. Since you've already paused and you still need another hint, let's give you another hint. Well, we know all these items. And we also know, if you got it, you can pause now and try it again. But we also know that we need to use this formula, right? But this formula, we know that V1 and V2 are equal, or that they are the same, and they're equal to 9 meters per second. So what we can do is we can plug in. If you haven't tried it yet, we're going to have a before kinetic energy and an after kinetic energy. I want you to pause the video and try it now. Alright, now that you've paused and tried it, let's check your answer. So we're going to plug in all of our numbers on the left, plug in all of our numbers on the right. You notice we've plugged in 9 for our 9 meters per second here. We're going to get our answer on one side, 105,000 and 81,000. There's a difference there. So we calculated the kinetic energy before and after the collision. This is before, this is after, and then it says the loss of kinetic energy. Well, afterwards, it's a little bit less, isn't it? In fact, the difference is 24,000 joules less, or 24 kilojoules are lost. Pretty cool stuff. So in summary, for collisions then, we reviewed that momentum is always conserved in every case, but not always energy, right? We've looked at momentum. We even reviewed a little bit of SUVAT. And we looked at some types of collisions, elastic collisions and inelastic collisions. And for those elastic collisions, we wrote an equation, this first equation. For inelastic collisions, we wrote the same equation, but now because they're combined, their final velocity is is the same for both of them. For kinetic energy and elastic collisions, kinetic energy is conserved in all cases. And for inelastic collisions, energy is not conserved, or kinetic energy is not. But how do we find that kinetic energy loss? Well, we just did an example of it. We find the final velocity using the conservation of momentum, or find that missing part, and then we calculate the difference in kinetic energy before and after. I hope this video is helpful.